Welcome. Today I will start water exchange reactions. Water exchange reactions. So it is a uh, applications of kinetic stability of coordination complexes that here we will look that how fast a water exchange reactions for the case of transition metal complexes as well as non-transition metal complexes. Water exchange means, let's say if I write any metals and we have that water 2 plus, let's say, and it to another water of 18. Then if you do the reactions, then M5H2O 18. So what is the rate? Let's say K1. Okay, if this is M1 metal and if I do that M2 metal, let's say K2, then now we will look that what is the rate of this K1, compare the rate of K1 and K2. Okay, so here how will you compare? By looking that what is the metal is there. Okay, by looking the metals and looking the charge, we'll compare the rate, whether K1 is greater or K2 is greater. So that will depends. So rate of metal, the rate of water exchange depends on types of metals or non-metals, metals, and also the charge. Okay, or also depend on the size. So how it depends, that we're going to look. So this is actually what you're looking, that previous class we have discussed and labile and inertness. It is the applications of that labile and inertness. For transition metal complexes, we see that where it is fast reactions, where it is slow reactions. If that is labile compounds, they are fast reactions. If that d orbitals has that labiles, that falls in the labile groups, then that is fast reactions. And if it is falls in the inertness, that d orbitals, then that is slow reactions that we have discussed for transition metal complexes. Here we will look water exchange reactions both for metals and non-metals. Okay, so for non-metals, generally what is found that water exchange reactions is faster in non-transition metal complexes. Metal complexes or main block elements than transition metal complexes. Okay, so here we will look that actual the experimental they found that this uh, this non-metals do that this amount of the rate, that we will discuss here. So So what we see that in previous class we have discussed that rate for metals and non-metals, for metal case and for non-metals, that is non-transition. It is not non-metals. This is transition elements, like that is transition elements, that is uh, D block elements, and non-transition elements, that is main block elements. What we see that for transition metal elements, that rate I have discussed that. First we look that whether it is labile and inox. After that, what we look that also, that if that is same, they have that electronic configurations. Then we have seen that rate or that we say labiles is directly proportional to charge, directly proportional to charge, and this is directly proportional to size. Okay, and for non-transition elements, that labile is that is also indirectly proportional to charge, and also it is indirectly proportional to size. Okay. So for transition metal complexes, if labile is indirectly proportional to charge, if high charge, then the labile is less, and if high size, then labile is high. But for that non-transition elements, both the cases it is inversely proportional. If charge is high, the labile decreases, and if size is also high, then also labile decreases. Okay, means that labile means that it's fast reactions, and inertness means we see that is slow reactions. Okay, so what we see here, we will classify that elements into that experimentally it is found that these elements have these rates, these elements have these rates. Okay, let me classify it. So before classifying that, we should know that in periodic elements this is somehow like this. So you see here that this is left, this is right. So left to right, that is size decreases, and this is top and this is down, and top to down size increases. So this size concept we will apply for this labile and inertness, and because we see that size and charge are important for taking labiles or inertness. Okay, so we see that here we have that here we have that earth metals and sorry, alkali metals and then earth metals. So here we have that, here we have Here we have alkali metals and we have alkali earth metals. Like where we have that compounds like lithium, sodium, this type of compounds is there, and here we have that beryllium, magnesium, this type of compounds are there, and here we have that transition metals like scandium, titanium, vanadium, chromium, manganese, ferrous, cobalt, like that compounds are there. Scandium, titanium, vanadium, chromium, manganese, ferrous, cobalt, nickel, copper, zinc. Okay, here p block elements. This is that a modern periodic table somehow look like this. So now we use this concept of size because here we have the size. Okay, so this is how. So have to look at where it is located and how its size is. Okay, so what is say that water exchange reactions, water exchange reactions is very fast. We will study that for case 1. Water exchange reaction is very fast, that is 10 raised to 8 second, this amount of rate. Okay, for this case and case 2 we have that water exchange reaction is moderate rate, and that is falls under 10 raised to 4 to 10 raised to 8 second inverse. Okay, and we have that case 3, that rate is nearly 10 raised to 1 to 10 raised to 4 second inverse. And for case this experimental results that rate is, that is 10 raised to minus 6 to 10 raised to minus 2, that is almost inert. It's slow reaction, slow. Okay, so this classifications, what you do that, so we know that for transition metal complexes we have divided into labile and inerts. So which are the labile compounds, means that is most labile compounds will comes in this category. Okay, so first we will look for transition metal complexes, then we will go for non-transitions. So transition metal complexes, what you see that which have that strong JTD, that will falls in the very past high labile, so that will be that like Cu2 plus, that is D9, and chromium 2 plus. Okay, this type of compounds will falls very fast reactions, and moderate reactions which will form, that is all the types which will be uh, uh, weak JTD they have. Or so we see here that for labels two things are important. One is charge, another is size. Charge also important and size is also important. So from this periodic tables we see that from this left to right, size is decreases. So here we see that scandium, titanium, vanadium, chromium, manganese, ferrous, these all are from here to here size is decreases, and if size decreases, then for labiles this is sorry. So labile means that there has to be a small size. High size, then there will be that inertness will come. So this is also indirectly proportional to size. Okay, so for this case, for this, then that is high size, then they are more labiles. Okay, this is directly proportional to the size, because for non-transition metals, if what you see that inertness is directly proportional to charge and indirectly proportional to size, then labile will be just opposite, that is indirectly proportional to charge and directly proportional to size. Okay, note that for this, for transition metal complexes this, and for non-transition metal complexes this. Okay, so for labiles they are directly proportional to the size. If size increases, then that will become more labiles for case of non-transition metal complexes. And for transition metal complexes, that is indirectly proportional to charge, both the cases. But for that non-transition metal complexes, labile is also indirectly proportional to size, means size should be low. Okay, so from here to here size is decreases. So what it found here is that here for type 2, so we see we need that charge is also low. So what is not that all plus 2 charge, all 3D transitions metals of plus 2, this states, except what we see that some are become inerts like, that is inert compounds are D3 and D6 are inert compounds. So D3 means that is B2 and D6 means Fe2 plus. Okay, so these are that these compounds are generally inerts, and if it is low spins, then, and if it is high spins, D6 high spins, then it is more labiles, this is equal to D1. Okay, so what we found that, so this will become more labiles, and water is weak pid ligand, so this will become that high spins, so this will become more labiles. So it is found that all transition metals except this D1, because they accept this B2, because this B2 plus that will become D3, and that is become and we know that D3 is always inert. So all 3D means D6 also fall, Fe2 plus also fall, except B2 plus. Okay, uh, Fe2 plus everything will fall in this S2, means that rate is 10 raised to 4 raised to 10 raised to 8 second inverse. So, and if it is low spin, for the low spins we see that this charge should be high, and this for our that ligand should be different, but we are taking ligand is water, so D6 always become high spins, and to get low spins either charge has to be high. Okay. So all 3D transitions metals are plus 2 except B2 plus. Also in this category what we have seen that this BBT concept, we see that titanium 3 plus, that is scandium titanium, that is D2, and 3 plus means that will come that D1. Okay, so we see that D1 and D6 are labile, so this titanium 3 plus also come, and also we have that is lanthanides also fall in these categories. Trivalent lanthanides also fall. Trivalent lanthanides. And for this case 3 case, case 3, that is rate is 10 raised to 10 raised to 1 to 10 raised to 4. And for case 4, 10 raised to minus 6 to 10 raised to minus 2. And for case 3, which type of transition metal will fall? That all 3D transition metals with +3 oxidations, means +3 oxidation state, and that is except the case of we see that is, if I say that, so where it comes now D6, this D6 low spins, this will not fall because this will be that we see this is highly inert except this D6. So where D6 will come, if cobalt 3 plus, then this will come D6. So cobalt 3 plus will not comes here except cobalt 3 plus. And if we have that chromium 3 plus, then what we have, that each rs1, then 1 3d3. So this chromium 3 plus, except this all 3D transition metals with +3 oxidation states will fall here. After that, so this vanadium 2 plus, because that will become the lowest bits, but the charge is low. Okay, because but you see here that transition metal complexes charge should be low for labile or fast reactions, and the size should be high. So here what you see here for labiles, the size transition metal size should be low and charge also low. Okay, so both the case we need low for transition metal complexes. So since here that this compounds, the vanadium 2 plus, although this is D3, but that size, but the charge is +2, size is +2, so charge is low, so this will fall in type 3 case. Here it will fall. Okay, and for that case 4 case, here all that the compounds like this cobalt 3 plus, which are highly inert, chromium 3 plus, and also the compounds transitions metals with 4D or 5D series, because if they have that, this are the very high size. If this high size, then we see that this will be that for lavables for transition metal complexes, that has to be indirectly proportional to size, also indirectly proportional to charge. So if that is high size, then lava will decrease. So these are the high size. So this all falls in this comment. This is almost inert. Almost inert. Here it will falls. These are about of these transitions metal complexes. So we see that where which groups will fall. Okay. So this how we will look by we have discussed already for that size. So for transitions metal complexes that lava inerts. According to that, we have uh, classified there what should be the rate. Okay. Also, you can look here also that you are looking strong JTD, and here we see that for the case of the vanadium 2 plus, this is D3, and ferrous 2 plus, this is D6. So this is high spin, so this is nearly equal to D1. That's why it will fall in this group. Okay. Also, you see that from this size also you can explain that this is high size, size is decreases, so this has the low size and vanadium has the high size, and high size will be less levels. That's why also this vanadium will not fall in these groups, and it will fall in these three groups. Okay, so this is about of the transitions metal complexes. Now if you go for non-transitions metal complexes, and what experimentally found that non-transition metal complexes do fast water exchange reactions compared to the transition metal complexes. So here for non-transition metal complexes, that is main groups, what you see that here that size is high. So both the cases of transitions and non-transitions we explain with the help of this periodic properties, that is size. Yet here size increases, yet here size decreases. Okay, so now for the case of non-transition metal complexes or non-transition metals or main block elements, see that lithiums. So this has that high size, because from left to right size decreases means this have the high size, and size is favorable for the levels for non-transition metals. That is, here we see that this is directly proportional to size. So this high size will have that high levels. It means these groups, alkali metals and alkali earth metals, will fall in the first categories. Okay, so here I will write all alkali metals and also all alkali earth metals. But we see that from here to here size will be decreases, here to here size is decreases. So in this case all will fall in the case one, but for this case what you see that all will fall except this and this. Why? Because we see that from top to down also size is increases. So this will have the top side, so this should have less size compared to these elements. These elements have the high size, and this will have the low size, because top to down size is increases. So top have low size and down have high size. Here to here size is decreases. So this will falls in the low size categories, because this will fall all are in the high size categories, because they are fully in the leftmost part, but these are after this will come. So this size somehow decreases from here to here. Also from top to down size it increases. So this top has little low size. It means that these two elements fall in the low size categories compared to this and this. Okay, so that's why what we say that this will not fall in the first categories. Also we see that this is the topmost groups for that alkali earth metal. So this will have that very low size compared to this. Okay, so this will be fall, this will be very low levels, and this is little high levels because this is compared to this is down, and from down size it increases. So here all alkali earth metals except beryllium 2 plus and magnesium 2 plus, and this magnesium has a little bit high size, so this will fall in this category Mg2 plus, and this beryllium is very low size, so this will fall in this category beryllium 2 plus. Okay, this much. Also here for case 3 it will have that aluminium 3 plus, 3 plus and gallium 3 plus. This will fall in these categories. Why? Because this aluminum, this boron, aluminium, this gallium, this block they will fall. So also charge is high, and they have also size is less. So this will fall in the third categories. So this is that somehow some experiment results they found that these groups of elements will have do the rate that is nearly 10 just to 8 second in the inverse, and this falls this in categories. Okay, so this how we classify it. So this only helps to understand, that how to classify that Laval and inertness. So for tungsten metal complexity it's very easy because that Laval and inerts compounds, and we know that rules. And for non-tungsten metal complexes we have to remember a little bit about of this. Okay, so this alkali metals and alkali earth metals, that's why, because they are falls in the left side, so they have high size, that's why they will fall in first reactions categories, and that magnesiums will fall here and these groups. And so from concept also we can understand that why these particular elements fall in these categories. Okay, so these are that highly inertness compounds will fall here, they are highly inerts, and these are strong GTD, this type of groups. So I will solve some examples. Arrange the following metal ions in increasing order of their water exchange reactions. So order of water exchange reactions. If we have that chromium 3 plus, vanadium 3 plus, ferrous 3 plus, and titanium 3 plus. Okay, so arrange that water exchange reactions. So we see that chromium 3 plus, this have that is D3, and it will false scandium, titanium, vanadium. Scandium, titanium, vanadium. Okay, so that is RS1 today. Scandium, titanium, vanadium, chromium, manganese, this ferrous. So this will fall. This is 21, this is 22, this is 23. So this will be D3. So this will 1, then this will fall in the D2, and this is falls in the D5, and this is titanium 3 plus, that will falls under D1. Okay, so now if you want to arrange water exchange reactions, so these are all transition metal complexes. So for transition metal complexes, what you see that first this D2 will comes here, then the groups of, because everywhere size is same, first D2, then we have that D1, then we have that is D5, then we have D3. So that is vanadium 3 plus, then we have titanium 3 plus, then we have 3 plus, then we have chromium 3 plus. This is the water rate. Similarly, if we take another examples, let's say we have that vanadium 2 plus, nickel 2 plus, manganese 2 plus, ferrous 2 plus, and copper 2 plus. So here that vanadium 2 plus means that is scandium titanium vanadium, that is D3, this is the D8, and manganese means this is the D5, and this is D6, and this is D9. So order how will comes, so this will give the strong JTD, this is strong JTD, so highly labile, and this weak JTD that we have already discussed, so this is also labile, and this will be the inert, this is also inert that we have discussed, and this is all in between. So now how will be the order will be, first copper 2 plus will comes, after that Fe2 plus will comes, after that this manganese 2 plus, then we have that nickel 2 plus, then we have vanadium 2 plus. This is the rate order. Okay, and if so we explain in terms of weak JTD and strong JTD. So we can also say that according to size, so this is size also you can explain that this is due to the strong JTD, so this is always high because this is strong JTD. And here we can also explain either we can explain with the help of JTD, also we can explain according to the size also. So here we see that scandium, titanium, vanadium, chromium, manganese, ferrous, cobalt, nickel, copper. From here to here, but size decreases, and we see that for labiles size should be decreases. So here we see that, and labile is indirectly proportional to size, means they need that low size. It means that this will be inerts according to size. Okay, because inerts is directly proportional to size, so this is high size, so that's why this is fall here according to size also you can explain. And we have that ferrous, this is low size, after that this is okay, so that's why this will low size will comes, this is ferrous, then manganese, and then this nickel. And for this nickel, so we can explain on the case of that tungsten metal complexes. Okay, so this will we look according to size. Also, if you know, this is also, it is very we can explain according to size. Also, if you know that labile nodes, then it is very easy to explain. Actually always remember that labile nodes accordingly we will explain. and actually this is on the basis of size and on the basis of JTD. And if you simply remember that Laval's and Inot's that order, then we can easily explain it. So this is due to strong JTD, this is weak JTD, and this manganese that will form here, that order we know that for transition metal complexes D5, after that D8, then D3. Okay, so that we already discussed in previous class. So today after this, thank you.